Going on, my math people? Alan here for another episode of trigonometry. This time we're moving on to a French fella by the name of de Moivre and the theorem that he came up with based off of the last application that we did in the previous section video, which was multiplying complex numbers in that polar trig form when they are raised to a power. Right? So we're going to talk about what those look like as well as applying it in its root form instead. So for that, I'll have to do a little bit of algebra review, but other than that, hang with me here. Some of this should look similar to things that we've done in the past when we had a multiple angle equation and we're trying to solve like a 4 theta or 3x, and it had 3 or 4 times as many answers. So just a quick little background on some of the stuff that we've already covered, and then we'll go into his theorem. I'll derive it for you at the beginning of this. If you don't care for the derivations, hopefully you figured out by now, skip through the first 15, 20 minutes and just get right to the examples. So hopefully you remember, we talked about how to multiply and divide those complex polar numbers, whether they're written as the r cosine theta plus I sine theta or r cis theta. And that last example that we did talked about what happened when we raised them to the power. And we saw a pattern there that the namesake, de Moivre, actually discovered before us. And so we're going to just be finding some of the different applications of that rather than this scenario because it's just less to write. So hopefully you guys are okay with using cis rather than cosine theta plus I sine theta. I like my cis, so I'll continue to use it. I see you, sis. So with this, I just wanted to give you a little picture of what he looks like. Let me move it up there, maybe. Oh, yep, no, it's still him. So yeah, that's de Moivre, and he's the one that actually discovered this first. So pretty nice little way for us to use these things, but in the real format that we're going to be using is not so much just raising some number to a power, it's more to find roots. And so this first thing that we're going to be looking at here before we derive it is, what if we wanted to find the nth root of some complex number? And so what this very succinctly says is, if I had some complex number, right, because we have a real and imaginary part, which makes it complex, and it was raised to the nth power, then how would I find all of the roots, the answers for this thing? Well, we know that in order to take something to the nth power and get rid of that, we would have to take the nth root of both sides. And so virtually what this is saying is that this a plus bi complex number would be equal to the nth root of its counterpart. So if you remember in the previous sections, we've talked about whether it's in rectangular complex form or that trig polar complex form. And sometimes on these examples, they're going to give it to us one way or the other. They even may request one form over another. So just remember that you know how to move the A and the B to R and theta if they give it to you in that rectangular form. But let me derive this for you so hopefully it makes more sense. And let's start with an example to do that. So if I wanted to deal with de Moivre's theorem, that meant that we could have anything raised to a power, and we knew that that meant that we would have that a plus bi, that complex number, times itself in times. But that would be a very arduous task. We would have to multiply, FOIL, distribute all of this out, and simultaneously simplifying it all until we got our final answer, which when we multiply complex numbers, we expect to get a complex number back. So what de Moivre discovered was, well, if I knew that form of my complex number that's currently in rectangular, and I applied it to its polar counterpart, then what I would be able to do is, instead of having to multiply it all out and FOIL and distribute and simplify, we could just take and use de Moivre's theorem, which said we would then have r to the n cis n times theta. So in order to use the nth roots theorem, our n is just going to become a fraction, because hopefully you remember a square root of anything was equal to the 1/2 power. We still have 1a, but we're trying to take the square root. So we needed something squared, something twice. And if we only have one, then that means we have half of what we need. If we took we call that the cube root of anything, then it would be written as a to the 1/3. So no matter what was inside of there, if we raised it to the 1/n, that was the same as writing it as the nth root. So for our first example here, to kind of derive this with you all, what if we were asked to find 3 complex, or what we call cube roots of some number, which I'm going to go ahead and write it in its condensed form, 64 cis 225. And if I'm looking for the cube roots, then virtually what that would look like in an equation would be something like, well, what cubed gives me that? Which means we would then have to take the cube root of this. And if I did the cube root of that, I would get my 3 possible answers, which is what the degree of the equation tells me. The problem is this is only going to yield one answer. But if you remember, 225 degrees is actually located at 180 plus 45 more right there. And hopefully you all remember that when we apply de Moivre's theorem to that thing, which is in polar form, our r cis theta, instead of writing it to the whole thing with a cube root or radical, I can raise it to the power of 1/3. And de Moivre's theorem would then allow me to take this thing and rewrite it in an alternative form, which would be raising my r to the 1/3 power, which, by the way, is the same as taking the cube root of 64. So I get 4. Cis, when I put the 1/3 in front, that means I'm going to be multiplying by 1 and dividing by 3. And when you take 225 and divide it by 3, I know 3 goes into 22 7 times, but that would give me 21. So I'd have 1 left over. I'd bring down the 5, and I know 3 goes into 15 5 times. However, that just changed my original point at 225 to a 75-degree angle, which we know would be somewhere over here. Now, don't forget, we talked about these things called coterminal angles that allowed us to take and add 360 degrees to get all the way around to that. Now, a common mistake that we talked about when we were doing this a couple of sections ago was that when we added 360, we couldn't just add it to 75, because then we were outside of that realm of 0 to 360, which is what they usually wanted all of those answers in between. And so we're going to have to take that 360, and just like we did with the 225 over here, we're going to have to divide that by 3. And remember, we can go around that circle as many times as we want to get back to that same point. We call those coterminal angles. So we can do that any number of times that we want. And hopefully you remember when we had 4 theta, 3 theta, 5 theta, and we were solving those trig equations with a multiple angle, then we would have, say it was 5 theta, we would end up having 5 answers. And so we would let n equal 0, 1, 2, 3, and 4. All right, so oftentimes they'll call it k right here instead of n, and they'll say it'll always go up to n minus 1, whatever your number coefficient is in front of your theta. So a lot of similarities here. That's what we're going to be dealing with for De Moivre's theorem, all right, is simply doing a lot of the same things. But instead of calling these x's, we're going to use z, all right, in order to find the number of roots. And in order to do that, we will take our r cis theta, we call it polar form or trig form, and we will raise it to the 1 over n. And as long as we can do that, like we did previously in some of those other sections, then we will be able to apply De Moivre's theorem like we always had, but now we're going to be finding the roots. So this would then give me r to the 1 over n cis 1 over n theta, which I could also write as theta over n. Now there is one issue with that. Remember, that would only yield one answer and only one answer, no matter if it was a square root, cube root, third root, right? Or any root. We need more than that. And the way that we did that in trig, we said, was by finding coterminal angles, which is by adding that 360 as many times as we want. So in order to get this, I'm going to backtrack just a bit, and I'm going to remove this ending parenthesis, and I'm going to say, well, I know I'm going to have to add to that angle theta 360 a certain number of times. And if I had that still raised to the 1 over n, then if I go to apply this like we did in the previous to the r, which would give me r to the 1/nth or the nth root of my radius, then I would also have to apply it here, which would give me that, meaning that I would have to have that 1 over n, and I'd have to apply it to both of these. So that's why they'll oftentimes call this number here or letter here k, all right, so that the n's don't get mixed up. And in order to do that, then I would have one more step to rewriting this, and we could write our final answer for all roots. It would be, for my angle, theta over n plus 360 over n times k, where remember k is equal to 0, 1, 2, all the way up to n minus 1, where n, remember, represents our nth roots. So pretty cool. We're going to be dealing with actual numbers like I started with here when I go through a few examples. And again, sometimes they're going to give us the form that we prefer, which in this case is that trig polar form. Other times they're going to give it to us in rectangular form, which means we're going to go ahead and try to rewrite it in a simpler form. And that's polar. So just to recap, this is what it would actually look like for your notes in a little bit condensed form. And they're using alpha instead of theta, because remember that angle theta that they originally gave us here and here is going to change. And so they're rewriting it as this, which again, I prefer this form. And we're going to end up taking the nth root of our r, raising it to that power 1 over n. And then that alpha, remember, we're going to take that original reference angle and we're going to add 360 to it as many times as we have to, while also remembering to divide both our original theta reference angle and that 360 that we're going to add to get coterminal angles by that n. Okay, so again, hopefully that does look very familiar to you. We did this in a previous section when we were solving equations where the angles were more than just one theta. So hopefully this does resemble something that you feel like you've mastered in the past, because we're going to be applying it. I'm going to show you what would happen if you tried to not use this De Moivre's theorem, which I highly do not advise. because what this is saying to do is you would actually have to take that number, that complex form, and multiply it out times itself 5 times. And good luck with that. It does not mean that you just get to raise root 2 to the 5th and I root 2 to the 5th. So be very, very cognizant of the fact that I know this seems a little bit weird and like a lot of work, but trust me, it's a lot less work than foiling, distributing all of that out, simplifying it, and then doing it again for the next, and then the next, and then the next. It would be very arduous and probably make a mistake, if not in one place, multiple places. So instead of doing all of that, we're going to take and we're going to rewrite this in its alternative form, which is what we worked on previously. So remember, the drawing will definitely help you. And I know that these are both positive, so I know I'm in quadrant 1. And since I'm in quadrant 1, I will march to the right a length of root 2, and then up a length of root 2. And since those are the same, remember this used to be my x and y, now it represents my real number, which was root 2, and my imaginary number, which is also root 2. And because they are both root 2, I know when I go to draw this in, I have a 45-degree angle there. And because this is a 45, 45, 90, I should know that this is equal to A, this is equal to A, and therefore this would be equal to A root 2, which means I have the square root of 2 times the square root of 2, or a length of 2. So I've now found my R, and I know my theta. So I can rewrite this whole thing, which is to the 5th, as R, which is 2, cis theta, which is 45 degrees. And now we can apply de Moivre's theorem to this. Much simpler than doing what I originally had up and raising root 2 plus I root 2 to the 5th, or multiplying it out times itself 5 times. Now I just get to write this as 2 to the 5th. Cis, remember that now comes down in front, and I get 5 times 45, which I set it that way on purpose. I can do 5 times 40, and then I can do 5 times 5. So 2 to the 5th, hopefully you know, is 32. So I now have 32 cis 225, and that's my answer. However, that is my answer in polar form. They, of course, wanted it in the form that they gave it to you in, which was rectangular form. So I do have one more step, but it was well worth putting it in this form and then applying de Moivre's theorem, because now all I have to do is expand this out like we worked on previously. 32 of cosine 225 plus 32 times I sine of 225. And then I will just simply take the trig functions and evaluate them, knowing that we are in quadrant 3 for 225 degrees, meaning that both of these things will end up being negative something. And because we know that this is a 45-degree reference angle, I already got the negatives taken care of. So hopefully we all can see that the sine and cosine of 45 degrees is root 2 over 2. So doing a little bit of canceling here, I will then find, since these are multiplying, I can cancel negative 16 root 2 and another negative 16I root 2. And that is way faster and much simpler than doing what we originally said that we could do, and that's raising this whole thing and distributing, foiling it out, simplifying to get that answer. And so in this example, they're asking us to find the cube roots, which tells us that there's 3, kind of redundant, but trying to help you on this first example, of this number, which can be complex, of negative 8. And of course, they said to write the final answer, the roots, in rectangular form. So I can actually write -8, which right now has only got the real part. I can make it complex by adding in however many imaginary parts. And since there's nothing listed, that means that we would have 0. So if I was to go back to my graph, which we've talked about many times, helps us see what we're dealing with. And if I was to plot this complex number of -8 plus 0 i's, where would I end up? On the x-axis or real axis, left 8, up and down, none in the imaginary, which means I should already know my radius and I should already know my angle theta. My radius would therefore, how long would I have to go out to be left 8? I'd have to march 8. The left is just because of the negative. The theta, therefore, also puts us at 180 degrees. So when I'm looking at the cube roots of this thing, I'm looking for all the roots, any of them, which happens to be 3. I'm going to write it as n to represent any of them. And if I can write this, then I should be able to put in that 0, 1, and 2 for the k in order to find all 3. So I've found my r is 8. Cis, I'm putting it in polar form, theta. And because it's cube roots, I know that I would raise this whole thing to the 1/3 power. So in order to get my answers, don't forget, before I actually apply de Moivre's theorem, I'm going to do one extra thing to this because I need 3 answers. And right now, this is only going to give me 1. And so to get back to this point, we said that we could take this form and add 360 any number of times we wanted. And so again, whether you use n or k, it's totally up to you. Not a big deal. To be consistent, I'll use k. But we had this whole thing raised to the 1/3. And now, because I have all of my answers, I don't necessarily like this being there. So my next step is going to be to write it out by applying de Moivre's theorem to this, which would mean 8 to the 1/3, or still have 8 to the first here. But remember, I have 1/3 of as many as I need. So that's going to be the cube root of 8, which hopefully you remember is a 2. And then I got cis. And then remember with the angles, we bring the 1/3 and we put it in front. So I'm going to be taking 1/3 of that and 1/3 of that angle. And we know 1/3 of 180, really nice, gives us 60. Plus also pretty nice, 1/30 of 360 is 120. And we said that we were going to let k equal 0, 1, and 2 because of the cube roots. Once you have found that, then you're on your way to finding all 3, but don't forget they wanted everything in rectangular form. So we do actually have to finish this. The cool thing is I know every single one of my answers is actually going to be, all 3 of them, Z1, Z2, and Z3. He is French after all, right? So I think they used it that way, de Moivre. Z1, Z2, and Z3, we know that 8 to the 1/3 is the cube root of 8, which is 2. The radius of these is not going to change. The cis we'll have to expand and deal with in a minute, but to get all of my angles, which is going to be the parts that differ, I'm going to start with my reference angle of 60 degrees, which remember was originally 180, but we had to apply the 1/3 to it. But I'm going to add that 120, which remember was also originally 360 that we applied the 1/3 to. I'm going to have to do that just one time around and then a second time around. So when you add 120 to that, you will then get your next one. And so when I add 120 to that, I then get 180 degrees when I add 120. And then I'm going to add another 120 to that, which is going to give me 300. And notice all of my answers are still between 0 and 360 as they were when we were solving the equations with multiple angles. So this is where I really like you all to stop, because once you have found all of those answers, then I know, because we've already done it in previous sections, that you can expand this and write it out in its other rectangular form. So on my math lab or whatever program you're using, just make sure that you do actually multiply it out if they ask you to put it in that rectangular form. So remember that means 2 cosine of 60 plus 2I sine of 60. And then same thing here, but with the other angle. And then lastly, because then once you have that, then you will have your 3 roots, all right? So be careful with these. Not that difficult, but lots of little places that you can get confused and miss something here or there. And I'll warn you right now, the number one place that students will make a mistake is right here. And they will add 360 to your reference angle rather than doing it with the initial reference angle. So be careful. Remember, if it says cube roots, then you know that's how many roots or answers you should get. If it's fourth roots, fifth roots, same thing. All right. And again, this should look fairly familiar as we've done things like this in the past, but of course, in a different form.